Thank thank you for introduction and thank you for this invitation. My talk today is based on a joint work with Naito, which has been published in here. The title of the article is the same as this. First, let me introduce some basic notation. Let G be a finite dimensional simple real algebra over C. For simplicity, we assume that G is simply raised. For the non-simply raised case, using so-called folding technique, folding of thinking diagram, we can obtain the same result as a simply raised case. For simplicity, we assume that G is simply raised. Now let her be the Cartan subalgebra of G, and let Hj be the simple coroot of G. Okay? Define her R to be the R vector space spanned by the simple coroot, which is a real form of her. Okay? Denote by W the while group of G, where Sj is a simple reflection with respect to the simple coroot Hj. Now, first, let us review the definition of Mirkovi-Vilonen polytopes, MV polytope for short. First, let mu dot be a collection of elements mu w of her R indexed by W, indexed by the while group W. We say that this mu dot is a Gelfand-Goreski-McPherson-Selganova datum, GGMS datum for short. If for each W, an element of the while group, and J, an element of I, the index set of simple correlates, then for each W and J, mu W Sj minus mu W is equal to njw times whj for some non-negative integer njw. Okay. We call this non-negative integer njw the length of the edge between mu w and mu w sj. Okay. Mu WSJ SJW. NJW denotes the length of this edge. Now let mu dot be a GGMS datum. Then we define a convex polytope P mu W by this formula and call it the pseudo-while polytope with GGMS data mu dot. This definition is very complicated, but in fact, we know the following. The collection mu dot, this mu dot, gives the set of vertices of P mu dot, and hence P mu dot is identical to the convex hull of this set, the set of mu W. Therefore, if you feel this definition is very complicated, if you can replace this definition with this, okay? Next, a GGMS datum mu dot is called an MV datum, Mirkovi-Vilonen datum, if it satisfies the following conditions 0 and 1 for each W and distinct Ij, such that WSI is greater than W with respect to the Brewer order on W, and WSJ is greater than W. Let me explain condition 0. Assume that Si and Sj commute with each other. We define N1 to be the length of the edge between mu W and mu WSI, and N2 to be the length of the edge between mu WSI and mu WSJSI, which is equal to mu WSISJ, and M1 to be the length of mu W, length of the edge between mu W and mu WSJ, N2 to be the length of the edge between mu WSJ and mu WSJSI. Then we have M1 is equal to N2, and M2 is equal to N1. This is condition 0. Next, let me explain condition 1. Assume that Si, Sj, Si is equal to Sj, Si, Sj. We define N1 to be the length of this edge, N2 to be the length of this edge, N3 to be the length of this edge, and M1 length of this edge, N2 length of this edge, M3 is length of this edge. Okay. Then we have M1. This M1 is equal to N2 plus N2 plus N3 minus minimum of N1 and N3. P is minimum of N1 and N3. And M2 is equal to minimum of N1 and N3. And N3 is equal to N1 plus N2 minus minimum of N1 and N3. This is.
Can you explain how this is related to the definition you gave?
I'm sorry, definition of?
You say that this, you gave a definition a second ago, and then you said it applies to this.
Mm-hmm.
Is this part of the definition?
Yes. Yes. Mm.
Okay. That's okay.
Okay.
Can I take a look at definition again?
Eh?
Sorry.
Eh?
Can this definition be worded in terms of tropical Flutter relation?
Sorry.
Can this be worded as tropical Flutter relation?
Yes. Okay. Then let me explain the definition of MV polytope. A pseudo-wire polytope P mu dot with GGMS data mu dot is called an MV polytope if mu dot is an MV data. Namely, mu dot satisfies this condition and this condition. Okay. For a dominant integral co-weight lambda, denoted by MV lambda, the set of MV polytopes with GGMS data mu dot such that mu W0 is equal to lambda and P is contained in the convex hull of W lambda, where W0 is the longest element of W. We can handle MV lambda with a crystal structure for UQ gate check as follows. let P be an element of MV lambda with GGMS data mu dot. Then the weight of P, weight of this element P is defined by this formula, where E is the identity element of W. Namely, the weight of an MV polytope is given by the vertex corresponding to the identity element. Let me explain the definition of lowering Cashel operators. For an element J of I, we define FJP as follows. We know that there exists a unique MV datum mu prime dot such that mu prime E is equal to mu E minus Hj, and mu prime W dash, mu prime W is equal to mu W for all W such that Sjw is less than W with respect to the Brillouin order. The other vertices is determined by this condition and this condition and this condition. Other vertices are uniquely determined. Then we define FJP to be the MV polytope with GGMS data mu prime dot if it is contained in the convex hull of W lambda. And to be 0 otherwise. Next, let me explain the definition of the raging Cashel operators. For each J, we define EJP as follows. First, recall that mu Sj minus mu E is equal to Nje times Hj for some non-negative integer Nje. And Nje is nothing but the length of edges between mu Sj and mu E. If Nje is greater than 0, then there exists a unique MV datum mu2 prime dot such that mu2 prime E is equal to mu E plus Hj, and mu2 prime W is equal to mu W for all W such that Sjw is less than W. We define EJP to be the MV datum with GGMS datum. We define EJP to be the MV polytope with GGMS datum mu2 prime dot if Nje is greater than 0. And to be 0 if Nje is equal to 0. This is definition of the raging Cashel operator. Finally, define epsilon j and phi j by these formulas, as usual. Then we know from Kamenitza's result that the set MV lambda, together with these maps, becomes the crystal for UQ gate check, isomorphic to the crystal basis B lambda of the finite dimensional irreducible UQ gate check module of highest weight lambda. where gate check is Lagrange dual Lie algebra of G.
You assume which is symmetric.
Yes, in my talk, this is isomorphic to G. but non-Cypress case is this is not isomorphic to G. Of G. Namely, we have an isomorphism between the crystal basis B lambda onto the set of MV polytopes MV lambda. Now let me explain our result. First, our first result is a description of extremal MV polytopes. Let lambda be a dominant integral co-weight, and let x be an element of the Weyl group. Since MV lambda is isomorphic to the crystal basis B lambda, there exists a unique element of MV lambda of weight x lambda. We denote it by px lambda and call it the extremal MV polytope of weight x lambda. Our description of px lambda is as follows. The extremal MV polytope px lambda is identical to the convex hull of this set, where this is a subset of W consisting of elements less than or equal to x with respect to the Brillouin order. This is our description of the extremal MV polytope. Our second result is a description of Demazure crystals. Let lambda be a dominant integral co-weight, and let x be an element of the Weyl group as before. Denoted by V lambda, the finite dimensional irreducible UQ gate check module of highest weight lambda. Then the Demazure module associated to X is defined to be the UQ plus gate check module generated by the one-dimensional weight space of V lambda of weight X lambda, where UQ plus gate check is the positive part of UQ gate check. Okay. This is the definition of the Demazure module associated to X. We know from Kashiwara's result there exists a subset Bx lambda, B sub x lambda of the crystal base B lambda, which becomes the crystal basis of the Demazure module Vx lambda. We call this subset Bx lambda the Demazure crystal. Also, we know from Kashiwara's results that Demazure crystals Bx lambda are characterized by the following recursive relations. First, the Demazure crystal associated to the unit element, identity element E, namely B lambda, consists of the single element U lambda, where U lambda is the highest weight element of B lambda. Secondly, for X an element of W and J an element of I, such that Sjx is less than X, Bx lambda, Demazure crystal Bx lambda is identical to the union of G's set without zero. The Demazure crystals are characterized by G's recursive relations. Now record the isomorphism of crystals psi lambda from the crystal basis B lambda onto MV lambda. Define MVX lambda, MV sub X lambda to be the image of the crystal, to be the image of the Demazure crystal Bx lambda under this isomorphism. We give a combinatorial description of Mx lambda in terms of the length of edges of an MV polytope. For this, we introduce some notation. Denoted by RW0, the set of reduced words for the longest element W0. And let M be the length of the longest element W0. Also, let I, I1, I2, .im be a reduced word of W0. Then define WIL to be SI1 times SI2 times the SIL for L greater than or equal to 1 and less than or equal to M. And WI0 to be the identity element of W. In addition, for a GGMS data mu dot, we define NIL mu dot, which is a non-negative integer, to be the length of the edge between mu WI L minus 1 and mu WI L, namely NI1 mu dot is the length of between mu WI 0, namely mu E, and mu W called mu SI1. The length of this edge is denoted by N1 I mu dot. And Ni2 mu dot is the length of the edge between this vertex and this vertex, namely mu Si1, Si2. The length of this edge is denoted by dot, and so on. Now, our description of the Demazure crystal is as follows. Let P be an element of MV lambda with GGMS data mu dot. Then this MV polytope is contained in the Demazure crystal MVX lambda. If and this MV polytope is contained in this MV polytope P is contained in the Demazure crystal MVX lambda if and only if whole sum reduced word I1, I2, dot, 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 IM. There exists a subsequence IA1, IA2, IAP of I such that the length NIA1 mu dot and NIA2 mu dot 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 NIAP mu dot are all equal to 0, and SIA1 times SIA2 times dot 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 SIAP is equal to XW0. This is our description of Dimaggio crystal. We can easily show that if this condition holds for some reduced word I, then this holds for every reduced word. So we can replace this sum. We can replace this sum by every. Anyway, this is our description of the Demazure crystal. Our third result is a description of opposite Demazure crystal. Let lambda be a dominant integral covariate and X be an element of the Weyl group W. The opposite Demazure module associated to X is defined to be the UQ minus gate check module generated by the one-dimensional weight space of weight X lambda, where UQ minus gate check is the negative part of UQ gate check. As in the Demazure case, we know that there exists a subset Bx lambda, B upper X lambda of the crystal basis B lambda, which becomes the crystal basis of the opposite Demazure module V upper X lambda, which we call the opposite Demazure crystal. Also, as in the Demazure crystal case, the opposite Demazure crystals B upper X lambda are characterized by the following recursive relations. First, BW0 lambda, namely the opposite Demazure crystal associated to the longest element, consists of the single element UW0 lambda, where UW0 lambda is the lowest weight element of P lambda. And for each X, an element of the Weyl group, and J, an element of I, such that Sjx is greater than X, Bx lambda, the opposite Demazure crystal Bx lambda, is identical to the union, this union of G's set with R0. Now we define MVX lambda, MV upper X lambda, to be the image of the opposite Demazure crystal Bx lambda under the isomorphism psi lambda between from B lambda onto MV lambda. We give the following description of MVX lambda. Let P be an element of MV lambda with GGMS data mu dot. Then P is contained in the opposite Demazure crystal MVX lambda if and only if whole sum reduce word I1, I2, IM such that WIP is equal to XW0 with P the length of XW0. Therefore, mu WIL is equal to WIL W0 lambda for all L greater than or equal to P and less than or equal to M. This is our combinatorial description of the opposite Demazure crystal. In addition, we have the following polytopal description of the opposite Demazure crystal. Let P be an element of MV lambda. Then P is contained in the opposite Demazure crystal MVX lambda if and only if P contains the extremal MV polytope Px lambda, namely the convex hull of this set. This is our polytopal description of the opposite Demazure crystal. Here, it is natural to suggest the following problem. For an element P of MV lambda, does the following hold. P is contained in the Demazure crystal MVX lambda if and only if P is contained in the extremal MV polytope Px lambda. The assertion if P is contained in the extremal MV polytope, then P is contained in the Demazure crystal is false in general. We can easily give a counterexample to this assertion. How about the converse assertion? Okay. The answer will be given in the next talk. Okay, that's all. That's all. Thank you very much for listening.